So yeah, we're going to finish up talking about automata theory and parsing and all of that stuff, and we're going to conclude with Turing machines and then talking about computability and notions of computation and so on and so forth. So how many people here are familiar with the name Alan Turing? Or how many people are not familiar?
Heard the name briefly, but I'm not 100% who he was.
So Alan Turing, yeah, go ahead.
Oh no, I was done.
Okay. Yeah, so Alan Turing, he lived in the early to middle part of the 1900s, and he's sometimes considered, you know, sort of the creator of what we call a computer today. No one person does something like that, but he did a lot of foundational work on theories of computation and trying to sort of understand what it means to be able to perform an algorithm, you know, and follow a series of steps and sort of trying to add some rigor to these notions of what is an algorithm, what is a recipe. As someone said in chat, he also cracked the enigma. So during World War II, the Germans had an encryption system called Enigma. It was a physical box with a series of dials, and it had a keyboard and I believe, you know, like a typewriter printer output, and you could type messages on it and the messages would come out encrypted, and the encryption key was based on how you positioned this series of dials, and they change the encryption key every day. And so even if, you know, after a few weeks of analysis you were able to figure out what the encryption key was, it was too late. It had a 24-hour lifespan, and then there was a new key the next day. And so Alan Turing and a number of other people, mathematicians, were tasked with, you know, trying to find a way to crack this cipher, and he actually came up with a way to do this by building a machine that helped with some of these calculations. And he was a mathematician. And he was interested in sort of foundational questions about mathematics, including questions about computability and what things can be computed, and are there limits to what can be computed. And if you're going to analyze a question like, you know, are there limits to what kinds of things a machine can do, you need to put some sort of characterization on what you mean by a machine. What do you mean by you know, performing an algorithm? And so he came up with a theoretical model of computation, which is today called a Turing machine, and used this to study questions on, you know, what can be computed by machines and so on and so forth. And he's an interesting read if you want to read an interesting biography. Go look at Alan Turing, an amazing life, a very tragic end, for which the British government only recently apologized formally. But he was definitely one of the shapers of our current world. So we were talking about state machines on Monday, and we had this notion of a state machine as something that has a present state, an input, a next state, and an output. And those are, you know, the state machines we typically encounter in Engineering 250. And a Turing machine is a particular type of state machine. So so let's formalize this. Turing machines. And go ahead and send me an attendance note. So a Turing machine is a four-tuple of Si, F, and S0. So S is a set of states. And remember, a state is just kind of this notion of the current status of a system. So if the system has, some kind of memory, it's basically the contents of the memory. But it's a more generic concept than that. So think of an elevator as a state machine. So the current state of the elevator might be where it's located, right? Which floor it's on, which direction it's currently moving in, if it's in motion, or the fact that it's stopped. Which buttons have been pressed, and whether the doors are open or closed, right? And maybe that set of information describes completely the state of the elevator. And you could describe how you want the elevator to behave by making a table of what it should do in different states based on the inputs. And the inputs might be, is there somebody standing in the doorway? Is there somebody pressing a button? And so you can start imagining trying to describe the intended behavior of this elevator as a series of state transitions. If you're, currently sitting on the first floor and your doors are open and somebody has pressed the button 2 and nobody is in the doorway, then you should, output the signal to close the doors and drive the motors to pull the elevator up, and you should go into a state where you are between floors 1 and 2. And, so on and so forth. So state is sort of the current description of what the system is doing. So a Turing machine consists of states. It consists of an alphabet, which are the symbols that we can use. S0, which is an initial state, so it's the state in which the system begins.
What's F?
What is F? So F is actually, it's a mapping from S cross I, so the set of all combinations of states and alphabets, into this crazy thing. S cross I cross R comma L. And we're not going to worry about what this means. I'm just putting this down for completeness. But let's take a example of a Turing machine, and let's think about it in terms of an example and build it up. So and it's mainly about the states. The alphabet's not really all that critical. Well, it's about the function, but it's describing the states of the machine. So let's look at an example of a state machine in the form of a Turing machine. So I'm going to have S0, 0, S1, R. S0, 1, S1, R. And I'll tell you what this means in a second. S0, B, which is for blank, S1, 0, R. S1, 0, S2, 1, L. S1, 1, S1, 0, R. And S1, B, S2, 0, L. Alright, so this is an example of what the F would be. But here's all we have to know. So we need to know the initial state, which is going to be S0 in this case. And this machine, we can think of it as having an infinite spool of tape. Could be paper tape, could be magnetic. And there's a read-write head, which can read a single symbol from this tape and can also write a single symbol from this tape. And this tape is broken up into cells, maybe 1 inch apiece. And we have the capability of moving this tape to the right or to the left, 1 step. Alright, so here's how a Turing machine works. we have these transition rules which basically say if you are in state S0 and you find the symbol 0 underneath this read-write head, you should do the following. You should change to state 1, you should write a 1 onto the tape, and you should move to the right. If instead you were in state 0 and you found a 1 under the read-write head, you should move to state 1, you should write a 0 under the head, and you should move to the right. If you're in state S0 and you find a blank under the tape, you should move to state S1, write a 0 onto the tape, and move to the right. If you're in state S1 and you have a 0 or a 1, you do one of these things. If you're in state S1 and there's a blank, you do that thing, and so on. And so yeah, go ahead.
So it's essentially like the state, the inputs, the functions, and then what's the last one again?
So this is what you write onto the tape, and this is which way you move, left or right.
Oh, okay.
So current state, current input value, right, which is the value under the read-write head, new state, output value, which you write onto the tape, and also a direction to move. And if this was a physical machine, we would think about moving the tape. But when we're doing this on paper, it's a lot easier to think about moving the read-write head itself. So when we say left or right, that will mean, you know, sort of moving the thing that's reading and writing the tape.
So F is basically the instructions.
F is basically the instructions, yeah.
Okay.
And it's basically, you know, for each thing in S cross I, states crosses symbols, we've got a corresponding state, symbol, and either a right or a left. So that's the way we would write it, you know, mathematically using the language of set theory. But to work with it, it's easy. It's just to think of this set of instructions as a set of 5 tuples. Current state, input, next state, output, and how we want to move. For us, it's going to be the read-write head. So for this program, let's start off with a tape, and suppose our tape consists of a bunch of blanks. So it's an empty tape, but in the middle we find a 0, 0, 1, 1, and then a bunch of blanks. And I'm going to draw an arrow to show where the read-write head is sitting. So let's suppose that the head is sitting right here on top of this 0. And we turn the machine on and we say start off in state S0, and we want to know what happens to the machine. Alright, so in this current state, it's going to look through the entire table and try to find something that matches the current state and input. So the current state is S0, so let me make a note here. Current state is S0, and the input symbol is 0. So it's going to look for an S0, comma 0, and it's going to find it right here in the beginning. Okay, so what does this instruction say it should do? It should change the state to S1. It should write a 1 onto the tape, so this will become a 1. And then it should move to the right. So it's going to move the read-write head over to here. And that's it. It's executed the first instruction. So now the current state is S1, the input value is a 0. It's going to look through its set of instructions for an S1, comma 0. And it's going to find it right here. And this says, hey, you should change your state to S2. You should write a 1 onto the tape, so this becomes a 1, and you should move to the left. And now the current state is S2, the input is 0. It's going to look through its instructions for an S2, comma 0. And it doesn't find one. There's no instructions for if you're in state S2 and your input is 0. And so at this point, the system halts. and that's the end of the machine. So in the case where we started with a blank tape with a 0011, it changed these two zeros to a pair of ones, and then the machine halted.
Now, when you say halt, does that just mean it just stops, or that's like a segmentation fault kind of a deal? Like
It means it just stops. It stops looking at instructions. It stops moving the tape or the write head. So it's basically done.
Okay.
So if it completes the whole loop of instructions, you can't find one, but it's done. Okay.
Right, exactly. And most CPUs today still have a halt instruction, which will basically stop the CPU.
And what would trigger something like that today?
Usually,
Pretty much can't.
so on Unix, if you execute the shutdown command, it will do some housekeeping and then execute a halt statement, and that stops the CPU.
Oh, so like on Windows, if you just shut it down, it's not closing all its processes, right? Basically, so what it'll do, like you use the shutdown command, it'll do what it needs to do to shut everything down, and then it halts.
Mm-hmm. Yeah.
Oh, interesting. Okay.
Yeah. It'll also happen sometimes if something unexpected occurs. So, like if the power starts to go down and the system detects a power fail, it will write out some critical information and then it'll halt itself, because you don't want the CPU running when the power is too low to reliably execute instructions. So it'll just go into a halt state, and that keeps it safe. Sometimes machines will go to sleep, and sometimes there's a suspend command or something that will bring the system into a low power mode, but allow it to continue running later.
This question might answer itself, but this is the same principle behind like the halting problem, right?
It is, yeah, and we'll talk about the halting problem in a bit. The Turing machine was in some ways developed in the quest for understanding an answer to the halting problem. So this is all good theoretical material. All right, so let's look at a different initial tape. So suppose our tape began with a bunch of blanks, and then maybe a 1 1 and a blank and a 0 1 and then a bunch of blanks. And let's say it started right here above the 1. So our current state is S0, and our input symbol is 1. So we look for an S01, we find that right here. And it says if you're in state S0 and there's a 1 on the input, let's go to state S1. Let's write a 0, and let's move to the right. So we come down here. So now we're in S1, and there's a 1. And S11 says stay in state S1, write a 0, and move to the right. So now we're in state S1 and there's a blank under there, and we'll look for an instruction that says S1 and a blank. Well, if you're in S1 and there's a blank, let's change to state S2. Let's write a 0 underneath, and let's move to the left. And now we say state S2 and there's a 0 underneath. So state S2 with an input of 0, and there's no such instruction, so the system halts. And it changed those pair of 1s and a blank into 3 zeros, and that's what that machine did.
So on this type of machine, that's gonna keep those zeros basically?
So
or is it gonna start up again with 1 1 blank?
So if I were to start it again with this on the tape, it would start with 0 0 0. But really, we're as a theoretical computing model, we're just kind of thinking of this as, here's a set of instructions, here's an initial tape, let's run the machine, see what it does. And it'll potentially change the tape, move the read-write head, and maybe at some point halt.
Okay. It seems like with this math, this is why mainframes came first, because it runs your calculation until it hit a halt like this, right?
Mm-hmm.
Is that maybe just a wild guess?
Well, it's an interesting question. So by mainframes, are you talking about things that like only execute one job at a time?
Yeah.
So
that was what I thought a mainframe was.
So early mainframes definitely ran one process from start to finish, and then would run a second process, and so on. But I think some of the later mainframes still were able to multi-process. But it's not an exact hierarchy. But mainframes were basically like the really large machines. And microcomputers are, the things that sit on your desktop, and mini computers were kind of in between. I don't know if there were technically mainframes that ran more than one process, but yeah, if we think of the question as, running one job from start to finish, that's partially just a kind of complexity issue, I think, because being able to, share a CPU among multiple processes is a really complex thing. Right, you have a process, and your program has a set of instructions, and there's memory values that your program's reading and writing, and there's usually internal storage for things that we call registers, so local values of data, and there's a program counter which says which instruction to execute. And if we're partway through running this program and we suddenly decide, hey, we're going to spend some time on somebody else's program, we got to do something with all this information. We got to take the whole memory of instructions and data and save that somewhere. We've got to take the contents of all the registers that were being used and save those somewhere. And then take this other person's program, pull all of that into memory, reset the values of the registers to what values their program was using, and then tell the system to start executing. And outside of that, have something that's, got a stopwatch so that after a millisecond or 10 milliseconds, it sounds an alarm and the operating system takes over and says, all right, your time's up. Let's go back and run this process again. And that's just a really complex procedure. Whereas if you have a machine that's only going to try to run one job, it's really just, load the contents of memory, set the program counter to the beginning and tell it to start running. And that feels pretty close to, the kind of thing we're describing here. Load up a tape, load up a program, tell it to start, let it go till it halts. So yeah, there's probably some correlation there. Although on mainframes there was usually a CPU time limit. And so if your program ran for more than like 10 seconds, something would come in and kill it. And then you'd get a nasty note saying, you used 10 seconds of CPU time, your account's been deactivated. That happened to me once. So yeah, this is a very sort of crude model, right? It's probably hard to imagine what we would do with something like this. I mean, these are toy programs where we're just kind of illustrating how this works, but we can do some useful things with this. And when you start analyzing these and writing some of these, you start to get a little bit better intuition for how all of this works. And so let's write a program that will take something like this, and I want to invert it. I want to turn it into this. So I want something that just gives me a complement of an input string. And we may as well stick with S0 for an initial state. So what I'm going to do, I'm going to say if you're in state S0 and you have a 0, then let's stay in state S0, let's write a 1, and let's move to the left. If you're in S0 and you've got a 1, let's stay in S0, let's write a 0, and let's move to the left. And that two-line program should give me something that complements an input string. So if I'm starting right here, and I'm in state S0, I've got a 0. This says I'm going to stay in S0, but I'm going to change this to a 1, and I'm going to move left. So this will become a 1. If I'm in state S0 and there's a 1, I'll stay in S0, but I'll change this to a 0, and I'll move to the left. And this will change to a 1, this will change to a 1. And then the last step of this program will say I'm in S0, and I have a 1. Let's stay in S0, let's write a 0, let's move to the left. Well, now I'm in state S0 and I have a blank under my read-write head. I don't have an instruction for that. System will halt. And so there's a two-state or two-instruction Turing machine that complements a binary value on a tape.
So if you were to start this again and redo the process, you'd want to start it at the first spot again, and then it would complement out everything again.
Exactly, yeah. And suppose when I was done, I wanted to do that. Suppose I wanted to move my read-write head back to the beginning. Right? So I could add some extra information, like if you're in state 0 and you have a blank, let's go to state 1. Let's write a blank under there, and let's move to the right. Alright, so when I get to the blank, I'll leave a blank under there, I'll move to S1, but I'll be sitting right here. And so I'm going to add a comment, move right until you see a blank. So in state 1, if you have a 1, we're going to stay in state 1, write a 1, and move to the right. If we're in state 1 and we have a 0, we'll stay in state 1, we'll write a 0 and move to the right. If you're in state 1 and you have a blank, we'll move to state 2, we'll leave the blank there, and we'll move to the left. And so now, after I've gotten to my blank, I'm going to write the blank, move to the right, I'll be sitting right here. I'm in state S1, I see a 0, I'll leave my 0 there, move to the right. State S1 and a 1, I'll leave my 1 there, stay in S1, move to the right. Leave the 1, leave the 0, leave to the 1. S1 and a 1, I'll leave the 1, move to the right. S1 and a blank, I'll leave the blank there, I'll move to the left, and I'll go to S2, and there is no state S2 with a 0 or a 1 under it. I'll halt at that point, but my arrow is pointing over that least significant bit again. There is no option for saying don't move left or right, just stay where you are. But if I really want to do that, I can make another state which says go to the right, and then that state can simply say take whatever symbol you see, write that back, and go to the left. And the effect of that would be to basically, go back to where I was before that first move. Alright, so let's try a few more examples of this. Here's a 4-line program. So let's suppose our tape contains 0, 1, 1, 0. And we're sitting right here over the least significant bit. Alright, and our initial state is S0. So if we're in S0 and there's a 0, we're going to stay in S0, we're going to leave the 0 there, we're going to move to the left. Now we're in S0 and there's a 1. This says we're going to go to S1, we're going to leave the 1 there, and we're going to go to the left. So now we're in state S1 and there's a 1. This says stay in state S1, change this to a 0, move to the left. S1 and a 0 says stay in S1, but write a 1 and move to the left. And S1 with a blank, there's no state for that, and so we halt. And so this took the number 0 and 1, 1, 0, and it changed it into 1, 0, 1, 0. So any inkling what this operation is that this machine just performed? This is an Engineering 250 flashback.
It converted gray code to I don't know what it converted it to.
Yeah, that's close. So if we take 0, 1, 1, 0 and we complement all the bits and we add 1, we get this. This is the 2's complement of that. And there's a trick for doing 2's complement. The trick is start from the least significant bit and keep all of your bits intact up to and including the first 1, and then complement all the remaining bits. Well, that's what this machine does. Assuming we're starting over the least significant bit, if we have a 0, it stays a 0. And we stay in this state. If we have a 1, it stays a 1, but then we switch to a new state. So state S0 means we're moving from the right, looking for our first 1. State S1 means we found our first 1, and so now we want to complement. If we have a 1, write a 0. If we have a 0, write a 1. And so this is a way to do the arithmetic negative of a binary number by taking the 2's complement. And we can start extending this. For example, you know, we're supposing that you're starting off on top of this least significant bit. But that may not always be the case. You might have a bunch of blanks, but maybe you're sitting somewhere in the middle of this number. And so we could have, you know, a preliminary state before we start doing that 2's complement, whose goal would be to move us on top of this first digit. And we could do something like this, right? If you're in state 0 and you have a 0, stay in state 0, write a 0, move to the right. If you're in 0 and you have a 1, stay in 0, write a 1, move to the right. If you're in 0 and there's a blank, move to state 1, write the blank, and move to the left. And if this is the first state that you're in, is S0, this set of instructions will basically leave the tape unchanged, but will move you down until you get to the blank, and then move you one spot to the left. And so we could write, you know, 3 instructions that initialize the position of the read-write head to the least significant bit. Well, that works great if our read-write head is initially somewhere between here and here. But what if our head was sitting, say, over here on top of a bunch of blanks? What instructions could we use to get it over to here? Any ideas?
Could you say, like, if you're in state 1? No, you already got that going. Mm-hmm.
Well, forget about these. Let's write a new set of instructions. Suppose we'll start with state S0 again. But we want to deal with the case where we're sitting on top of a blank. In other words, we're too far to the right of our number.
Oh, okay, so if we're starting from the right and working back to the left.
Mm-hmm.
S0, if it's blank, stay in state S0. Leave it a blank, move to the left.
Cool. So that's going to, if we're sitting over here on a bunch of blank tape, it's going to leave the tape blank, but it's going to keep moving over. And then if we're in S0 and there's a 0, or if we're in S0 and there's a 1, we can do whatever we want to do and go to a new state.
Wouldn't there be a problem with that, though, once we got all the way to the left and we hit a blank?
So I would do this as a startup state. So now I would do something like, maybe if you're in S0 and there's a 0, let's go to S1, write a 0, and go to the right. If you're in S0 and there's a 1, let's go to S1, write a 1, and go to the right. And then in S1, we know we're going to see a blank, and so let's go to S2, let's write a blank, and go to the left. So at this point, if I start in S0, I know that eventually I'm going to end up in state S2, but when I get there, I'm going to be sitting right on top of that least significant bit. And now I could do, I could write these instructions for S2 for the instructions to say do a 2's complement, or, calculate pi, or whatever I want to do. So we're almost thinking of like, subroutines or functions in some sense. Certainly modularizing our code, where first we're going to have a set of instructions that will, if we're sitting to the right of our number, move us over to the least significant bit.
So in this example, since we're all the way over to the right, we're moving all the way to the left, we can basically set up the instruction as if you're in S0 and you see a 0 or 1, change to S1, and now you're in a totally different set of instructions, right?
Yep, exactly.
And then you don't have to worry about once you get to the blank on the left.
Right,
Okay.
right. And we could do the same thing if we happen to know that we were sitting here too far to the left. We could write a different set of instructions that would basically move over till we get to a 1 or a 0, and then keep moving until we get to another blank, and then move left 1 spot, and that would get us right here. So we could make a set of instructions for starting too far to the right, getting us here. We could make a separate set of instructions if we're starting too far to the left, get us here. Here's the question: what if we don't know where we are on the tape? What if we know that somewhere in this infinite tape of blank spaces there's a binary number somewhere, and we have no idea where it is? And don't worry too much about Turing machine mechanics as far as these instructions, but just kind of from a high level, how could we go about finding where this pattern of 1s and 0s is, where this binary number is in the middle of this infinite blank tape?
Just pick a direction, look for anything that's not a blank, and move in that direction until you find something. And if you don't, you get to the end, go the other way.
Ah, but there is no end, because it's an infinite tape. So that's a perfect solution with that one wrinkle.
So if there's no end, there's no beginning either?
There's no beginning either.
Okay.
But there is a way to do this.
Could you like have a step amount so that the first iteration you're gonna step to the right once, and then you, that increment moves to 2, so you step 2 to the left,
So you get the right and the left from where you were in the middle.
All right.
And then you increment it again, so you step 3 to the right.
Awesome.
And then 4 to the left, and then you get everything in both directions.
Awesome.
Constantly.
All right, you're all thinking like Turing machine programmers now. Right? This is initially a horrifying way to have to do this, but this totally works. Right? If we don't know where this binary number is on this infinite tape, we can start doing this increasing search in each direction. And, you know, if it's 1,000,000 spots to the right, eventually we'll get 1,000,000 spots to the right and see our digits. And if it's 1,000,000,000 spots to the left, eventually after 2,000,000,000 of these changes of direction, we'll find a digit. And then we know, oh, there's the start of our number. So it takes a different mindset, right? We don't have for loops, we don't have if statements, but we kind of have things that let us do something similar to those. And
That kind of is like an if-else, right?
Yeah, it kind of is, which is sort of fun. And these can be fun ideas to think about, right? And
funny how all the basic concepts keep showing up in more complex.
Yeah. Absolutely. And it turns out that, you know, anything that you can do with a C program or a Python program, you can do with a Turing machine. You can write a series of these Turing machine instructions and come up with a Turing machine program that will do, you know, whatever you want to do in a C program. It can do PA5 from CSE215 and make a word index on an input file, right? You can do all of that with a Turing machine. And it's more than just, you know, a Turing machine is powerful enough to do what an Intel processor can do. It's really the other direction around. The question is an Intel processor powerful enough to do everything a Turing machine can do? And if it is, then we say that that is Turing complete. And so when you study a new language, one of the questions that comes up is this language Turing complete? Is it powerful enough to do everything that this Turing machine can do? And it's not, because, you know, physical machines don't have infinite memory. But other than that, as far as algorithms and procedures, the question is, you know, is the language or the machine or the architecture Turing complete? Can it do what a Turing machine can do? And that's sort of the benchmark we use for a general purpose computer. It means it's at least as good as a Turing machine. But programming these things is not for the faint of heart, right? Because, you know, you'll go blind making tables like this and staring at them for too long. But it can be done. So you can find lots of simulators online. So this is one I like. It's a Turing machine simulator. That basically you can load in an initial input on the tape, so everything is blank except, you know, what you put in here, and you can type in a program. And so this is a bit of an augmented Turing machine. There's things like wildcards and stuff like that. There's also comments, right? Because comments are really useful in Turing machines. And you can run this. And as you run it, you can see the read-write head moving back and forth and the program executing and so on. And so that took 38 steps, and it basically turned an initial input string into a smiley face. And I don't know what it does with different input strings. I think it just goes through and it scrubs the tape and then puts in a smiley face. That's interesting. Magic the Gathering is Turing complete. I don't know what that means, but there is a computation going on. And by the way, since somebody else brought it up, Magic the Gathering is a really cool approach to a lot of things, like in Engineering 270, because there's, like, you know, a stack that you put your effects on, and there's instance, which used to be called interrupts, which basically act like interrupts in a CPU and stuff like that. And so yeah, lots of things have been proven to be Turing complete. So this is a fun little simulator, and it comes with some sample programs. So for example, binary addition. So this will add these two numbers together, and as it runs, you can see which instructions are being executed and how the read-write head is moving, and there's the sum of those two initial numbers. So I don't know, let's do 7 plus 5. So there's 7 and 5. And let's run that. And there's the answer, 12. 8 plus 4. And the more you start to work with this, the more you start to realize that you can actually write programs to do things, and you start finding yourself doing things like what you do with other languages. For example, with this, you'll see that, you know, even though we've got ones and zeros on our tape, we start getting new symbols popping up. That's a way to save information. And I think it's probably using those to say whether or not there's a carry being generated. But, you know, adding two numbers, two binary numbers, is a pretty straightforward operation, right? If you have two zeros, it's a 0. 0, 1, or 1, 0 is a 1. 1, 1 is a 0, but you need to remember that there's a carry, so that on this next stage, you have an extra 1 that gets added. And if your symbols are written like this, and you're starting over here, well, this is the first bit you're going to add. Move to the left till you find a blank, move one more spot. That's the second bit you're going to add. And you'll do that in one of two states based on whether this first bit was a 1 or a 0. If it's a 0, you're in a state where when you get to this, you're going to want to write out a 1. So you'll move to a state that'll eventually add a 1 to your tape. If your bit was a 1, you'll be in a state which says, hey, if I find a 0, write a 1. If I find a 1, write a 0, but also go to a different state that remembers there's a carry going into the next stage. And you can add other symbols onto the tape, which is what these X's are that are appearing. And there's a Y in there also. And so binary multiplication is a little harder. So let's do 7 times 5. And you know, multiplication, you've got a lot of partial sums you need to generate, which means you're doing that whole binary addition thing multiple times in addition to shifting over and keeping track of a running sum. But 7 times 5 should give us 35, so 1, a bunch of zeros, and then a 1, 1. And this is taking, you know, 400 some steps. And there we go. There's 32 plus 2 plus 1 is 35. And you can run this at full speed, and it goes a little quicker.
What's the name of this website again?
Looks like morphit.info/Turing. But I just Googled Turing machine simulation. This is the first one that comes up. And it's been around a long time. But it's that. And they were nice enough to give us a bunch of example programs in here. So let's do some prime number tests. So testing for a prime number, you've got to be able to do division, which is even harder than multiplication. And you need to be able to do repeated division by possible factors and keep track of whether you find a factor or you get to a divisor that exceeds the square root of the number you're checking. So let's see if the number 5 is prime. And we'll run this at full speed. Oh, I guess we have to hit that in the beginning. We'll run that at full speed. And it says the number 5 is prime, 1500 steps. Let's try the number 13. And this program's fairly long.
Is the time going up because of the number of bits we're using, and it's increasing by the number of bits?
Yeah, more bits, it's more possible divisors, and so it's got to do more iterations. But this was 9,000 steps for the number 13. If we do the number 15, it should find a factor for that probably sooner than 9,000 steps. When it tries to divide by 3, it should discover that it's not prime. But it is a bigger number. So that's a mere 6,700 steps to find out it's not prime. And this is, this is way worse than assembly language or machine code. This is just, these endless 5 tuples of state, input, output, direction, and new state. Plus, like I said, some wildcards that say, whatever symbol you have and so on and so forth. And some of it is comments, They put a synopsis at the top, so they got their 10 points for that too. So yeah, this is a pretty rudimentary way to do computation, but it's universal. Right? It'll let us do anything that we want to do. So that's sort of the essence of a Turing machine. And as I said, Turing machines were developed by Alan Turing in part in studying this question called the halting problem. And that's the English version of the name. I can't do justice to the German version of it, but this was basically one of David Hilbert's problems that he posed in the beginning of the 20th century. His set of problems that he asked mathematicians to contemplate. And one of them was basically a version of the halting problem. And the halting problem is really easy to state, right? If you're given a Turing machine program like this, right, and you're told what the initial value of the tape is, the question is simply, will the machine ever halt? Or will it run forever? And if I have a blank tape and I have a machine like this, and that's my whole program, it's never going to halt. It's going to be in S0, it's going to see a blank, it's going to stay in S0, write a blank, and move to the left. And it's just going to keep spinning my tape to the left. But it's never going to hit an instruction that it can't find. It's never going to have a state symbol combination that it can't find in here. And so this program will run forever. But the programs that we started with in the beginning, and these programs here, eventually halt. But it's not clear from looking at this set of, a few hundred instructions and this initial tape, it's not clear whether or not this is ever going to exit, whether it's going to halt. And so the halting problem is basically, can you look at a Turing machine program and an initial tape and decide whether or not the machine halts at some point? And in particular, when I say, can you make that determination, what's really being asked is, can you write a Turing machine program that will make that determination? So a solution to the halting problem would be a Turing machine program that you can give it a set of states and an initial tape, and it will, in some finite amount of time, give you an answer and say, yes, this halts at some point, or no, it never halts. And it doesn't matter how long it takes, but it has to answer in a finite amount of time. It can't run forever. And what Alan Turing was able to prove is that there is no possible solution to the halting problem. You cannot come up with an algorithm to make this determination in all cases. Now, in a lot of cases, you can. Just like you and I can look at a C program and we can say, will it ever execute that final return statement, or will it run forever? Well, if it's a while 1 equals 1 loop and there's nothing that breaks out of the loop, we can say, yeah, this will run forever. If it's a for I equals 1 to 10, do this stuff and then return, we can say this will return at some point. But there's no way to... Go ahead.
Couldn't you,
if you have states there, and one state contains essentially the instructions to halt,
Mm-hmm.
if that state is ever transitioned to from any other state, wouldn't that lead to a halt?
Yes, but how do you know that that state which transitions to it is actually a state you'll ever reach?
That's true.
And so it's a hard problem in general. And in some cases, we may be able to look at it and see, well, all these states lead to S3, and S3, no matter what the input is, will eventually cause a halt. But the general question is apparently unsolvable. And Alan Turing showed this several decades ago. And so there's limits to what a computer can do. And that's a really interesting thing to grapple with. Because to the degree that you believe that our minds are computers, that might suggest limits to what our minds can do. Limits to what we can think of. And that's an interesting possibility. And so, if you want to go home and try to prove that you can solve the halting problem, I think that's a fun exercise. And in trying to do that, you can start to see some of the problems that you come into with trying to answer this question in all possible cases. So that's the halting problem, and it's an interesting consequence of computing, that there's some programs you just can't get a computer to do. There's some problems you just cannot solve with a computer. And this is a pretty basic program, right? I mean, give me the source code for a C file and tell me what the inputs to the program are going to be and tell me if the program exits or not. And you can't do that in all possible cases. So that's a little bit weird, but it's going to get a lot weirder. So, so what we've been talking about, Turing machines are sometimes called deterministic Turing machines. And they're deterministic because, when you're in a certain state and you have a certain symbol under the read-write head, we know exactly what's going to happen. We find the instruction that corresponds to that condition, and that will tell us without any ambiguity, what's going to get written onto the tape, what the new state will be, which way the tape's going to move. Okay, it's completely deterministic. There's nothing random going on. And you can analyze, the same system a million times, you'll always get the same output. Right? And we think of computers as being deterministic, depending on what operating system you're running. They usually do the same thing every time. And so a deterministic Turing machine, or a DTM, is just, a plain old computer. It's got a set of rules that describe what it does. But there's also something called a non-deterministic Turing machine. Turing machines are theoretical, by the way, because of the infinite tape business. A CPU memory system today looks like a Turing machine, except the tape is finite. That's the memory, basically. A non-deterministic Turing machine is a totally fictitious entity, so far. It's a Turing machine with a genie inside. And it's usually a friendly genie who's there to help you. And what this genie will do is control what state the system goes into based on what you're trying to do. And one way to think of this is, suppose you're trying to see if a number is prime, right? So, is n prime? And so you ask, does 3 divide n? Does 5 divide n? Does 7 divide n? And you keep trying different numbers to see if any of these numbers divide n. And if you run out of numbers, then you say, oh, my number's prime. And if you happen to hit something that divides n, you can say, hey, it's not prime, it's got a factor. 11 divides n, so it's not prime. So imagine you had a machine that you could say, okay, generate some random number and see if that divides n. And this genie in the machine would make that random number always be a divisor of n, if it had a divisor. The first time you look for a divisor, you'd find out, oh yeah, 117, that does divide n. I guess n's not prime. So the genie in this non-deterministic machine basically helps you solve your problem. It will help you make good choices so that you shorten the execution time of an algorithm. All right, and we don't have machines like this today. We might someday. These might pop out of quantum computing for all we know. But right now, this is purely a theoretical question. Let's see, modern printers, straw ink. Probably not. Although I think our interpretation of a Turing machine is based on maybe dot matrix printers. I don't know if people remember those, but you used to have printers with paper that would come out along a set of tracks on the side, and there was an actual print head that would move left and right, and little pins that would come out of the print head as it moved and hit a piece of ribbon. That's the image I have in my brain when I talk about Turing machines. And I don't know what Alan Turing had in mind. When I learned about Turing machines, I was told it was a piece of magnetic tape and a magnetic read-write head. But yeah, maybe there's some tie-over from that to how dot matrix printers were conceived. All right, so why do we care about non-deterministic Turing machines? There's this notion of order of complexity. Order of complexity, we've touched on this a little bit earlier this quarter. Order of complexity is a notion of not just how long does it take to do something, but how much more time does it take to do something bigger. So if you have a problem that takes a certain amount of time, and now you take a problem that's twice as big, does it take twice as much time? If doubling the problem size takes twice as much time, that's a linear increase in time. We call that order n. If doubling problem size doesn't take any more time, that's a fixed computation time. That's order 1. If doubling the size of the problem quadruples the amount of time it takes, that's what we call order n squared. So if I have a problem 10 times larger, this would take 100 times as long. If doubling the problem size takes 8 times as long, that's an order n cubed. And these are pretty yucky. Right? Bubble sort, the first way we usually learn to sort numbers is an order n squared algorithm. It's a pair of nested loops. That's pretty horrifying. Some matrix operations will be order n cubed or n to the 4th. That's even worse. Because if I have 1,000,000 times more numbers, it's going to take 1,000,000,000,000 times as much time if it's order n squared. It's going to take 1,000,000 trillion times more if it's an order n cubed. But there's things even worse than this. So let's look at a class. Go ahead.
I said the factorial.
Yeah.
Factorial, that's the worst.
Yep. So let's look at traveling salesperson. This is a classic graph theory problem. And the idea is you have a graph with a series of points, and it's a complete graph. So you have an edge from every vertex to every other vertex, and you have distances on each of these. And the goal of the traveling salesperson is the following. You're selling encyclopedias, right? This is your home city. And you want to travel to all of these other cities to try to sell encyclopedias, and then you want to travel back to your home. And gasoline is very expensive, and so you want to minimize the amount of time that you have to spend traveling. So you want to find a path through here to visit every vertex and get back to the beginning with the smallest total distance, where these numbers on each edge represents distance. So you're trying to minimize the distance it takes to travel through here and visit each vertex and come back to the beginning. And this is the traveling salesperson problem. And you know, it may be that this city is, you know, 20 miles away, but the distance from here to every other city is humongous. And so even though it takes 20 miles to get to this city, my best bet at that point is to come back to where I started and then take some other road to these other cities. And so it's a pretty hard algorithm to come up with a way to find the best possible path. If you care about efficiency. If you don't care about efficiency, though, this is trivial. So let's say I have n cities. Well, let's just look at how many possible different paths there are from my starting point to visit all the cities and come back. And I can break this into a series of subtasks. My first subtask is choose my first city to visit. While I'm sitting here, I have n-1 possible choices. And once I get here, I have another n-1 possible choices. And once I get to my next city, I have another n-1 possible choices. And so on. And assuming I don't go back to where I started, and I only have to visit n cities, right? This looks like n-1 to the n. And when you do these orders of a complexity, we can do a lot of approximation. Constant factors and things like that go away. This would end up being on the order of n to the n complexity. And n to the n is way worse than n squared or n cubed. So we break our algorithms in terms of order or complexity into two categories. Dijkstra's algorithm will find the shortest path from one point to another, and that's an efficient algorithm. But the goal here is to find the total shortest path that lets us visit every vertex and come back to the beginning. And so we have to use Dijkstra's algorithm multiple times, and it may not be the shortest path from here to here. That's part of our final solution for the shortest total path. So we can categorize algorithms in two really broad categories. If the order of complexity is something like n squared or n cubed or n to the 10th, right, or n to some fixed power, we say this takes polynomial time. And polynomial time, it's not great, but it's not too bad. Compared to something like this, which is not polynomial time. It's much more complex. So with this notion of being able to perform an algorithm in polynomial time or not, we can take problems and break them into two categories. The first category is called P. And a type P problem means it's solvable in polynomial time on a deterministic Turing machine, a plain old computer. So we could write a C program that does this in some order of complexity, which is basically a fixed power of n. An NP problem is solvable in polynomial time on a non-deterministic Turing machine, a machine with a genie. And traveling salesperson is an NP problem. Because if we had a genie who could like help us make the right decisions along the way, we could do the following. We could add up all of the distances of all the edges. And they add up to some number like, I don't know, 3,247. And we know that if we travel along every single edge in here, the total distance is 3,247. So there's certainly a way to visit every city in this distance. And so we could write a program that basically asks the question, is there a way to visit all the cities in a distance smaller than 3,247? Okay, this is a yes-no question. And to do that, all we would have to do is, if we knew which paths would give us a shorter total distance, we could simply add up the lengths of those edges and say, yes, there is a distance that's shorter. And so on a non-deterministic Turing machine, we could ask our genie, is there a path shorter than this? And if the answer is yes, it should tell us that very quickly. And if there is a path shorter than that, right, it gives us the edges to add up. That's a fixed amount of time. Then we say, is there a path with a distance shorter than 3,246? And if it says yes, then we say, is there one shorter than 3,245? And we keep going, and eventually we say, is there a path shorter than 1,731? Yes. Is there a path shorter than 1,730? And if it says no, that's our shortest path. And this is, nominally an order n algorithm. There's some other factors, but this is solvable in poly time if we have the genie. So traveling salesperson is an NP problem. It's solvable in polynomial time on a non-deterministic Turing machine.
I have a question for
Yeah.
you. I've heard about this as big O notation, and I'm kind of curious about it because I'm fascinated with prime number calculators.
Yeah.
It seems like the complexity just goes up consistently as numbers get bigger. Would there be a notation for a problem like that?
Well, it goes up, but finding a factor for a number is, I think it probably is order n. Because if you double the size of the number you're testing, you basically double the number of factors you have to check. And if you have a number that's, 100 times as big, you have 100 times as many factors that you have to check. So even though prime testing is like really, really slow for big numbers, it's still an order n algorithm, which is not a bad computational complexity.
Would there be something to describe something else to describe like the increasing difficulty of it, maybe?
Something like a big O would be the primary way. Now, if you get to ridiculously big numbers where you can't just do division anymore, but you have to start taking your number and doing pencil and paper division inside the computer, that's an additional factor. And so you might try to describe the complexity of finding a prime number with n digits, where you're not just saying, take my number and divide by a factor, but you're actually writing the code to do the division bit by bit. And I don't know what that complexity would look like. But that's usually what the real issue is with prime numbers, is not, the CSE215 prime number test we do, but when you have something with 1,000 digits, how do we check to see if that's prime? And how do we do those divisions of 1,000-digit numbers? And I don't know what that would end up being. I think it would still be polynomial time. It would be n to some power. Alright, so two classes of problems. P, solvable in polynomial time on a deterministic Turing machine. NP, solvable in polynomial time on a non-deterministic Turing machine. There's a subset of NP problems which are called NP complete. And an NP complete problem is the following. It's a problem that's solvable in polytime on a non-deterministic Turing machine, but we have not yet discovered a polynomial solution on a deterministic Turing machine. In other words, we don't have a C program that can solve this in polynomial time. It might exist, but we haven't found one yet. And Traveling Salesperson is an example of that. We know that if we had a genie in the bottle, we could find a polytime algorithm to solve this. But we don't know if there's a way on a plain old, Pentium processor running C, if there's a way to solve this in order n squared, n cubed, n to the fifth, something like that. There might be, but we haven't found it yet. But the fact that it's NP complete means the following thing. It means that if we can find a polynomial time solution for this problem, we have found a polynomial time solution for all problems that are called NP complete. So NP complete is a family of problems that right now we don't know how to solve efficiently. But that if we figure out how to solve any one of those efficiently, that will give us a solution to solve all of them efficiently. And this is probably the most famous problem in computation theory, is this question of whether there is a solution to any NP complete problem. And if we can solve just one of these, if we could find a solution to Traveling Salesperson in polynomial time, there's a whole slew of problems that suddenly fall down and can be solved in polynomial time as well. And so from Wikipedia, here's a list of some examples of NP complete problems. And so there's some graph theory questions, three-dimensional matching, click problems, coloring problems. We talked about a few of the concepts in here: graph coloring, Hamiltonian completion, Hamiltonian path problem, directed and undirected, longest path problems. There's mathematical problems. We'll talk about partitions and knapsack problems in CSE215. There's formal languages, closest string, shortest common subsequence. There's games, Battleships Bejeweled, Candy Crush Saga, Donkey Kong, Pokemon should be in here, right? That have been shown to be solvable in polytime. Someone just mentioned in chat, yes, there is $1 million prize standing if you solve this. And you will also break the world, because this has pretty serious implications for cryptography and crypto systems, which are basically based on the difficulty of executing certain algorithms. And if you can find a way to execute those algorithms in polynomial time, all of the strong security we get from certain kinds of encryption suddenly fall away. And that encryption is no longer usable. So this is an open problem, and it's one of these problems where if you dig a little deeper into this idea of computation and non-deterministic Turing machines, you don't need, a doctorate in computer science to be able to think about these problems. And so this is a particular problem that's attracted a lot of attention from self-taught computer geeks like myself. And people, always come up with what they think are solutions and submit them to journals, and inevitably, there's a logic error in the attempted proof. But it's an open problem, and we don't even know if there is a solution to this problem, and if there is, whether it's affirmative or negative. But it's one of the fringes of theories of computation. All right, so we are at 151. So that's going to do it for lectures for this quarter. So Friday we will talk about the final exam. I will post a topic guide before then, and we'll basically talk about that on Friday. Talk about what to expect on the exam and any questions and so on. Yes, there is class on Friday, but it'll be a wrap up. It won't be a lecture on new material. All right. If you are still working on homework 10, go ahead and turn that in. I'll grade that probably tonight or tomorrow, and give you some feedback on it, and we can talk about those questions also. I might ask you some pretty high-level questions on Turing machines or state machine, string recognition, stuff like that. I don't think I would ask you to write a Turing machine program, but I might ask you to look at a Turing machine program and tell me what it does to an input string, that kind of thing. Check the final exam schedule on Clark's website, and whatever it says for 12:30, Monday, Wednesday, Friday classes, that's it. I believe it's Monday, but check the website to be sure. All right, go ahead and send me an attendance note on the way out, and have a great rest of the day. I will see everybody next time.
See you later.
All right, see ya.